Hello, thank you for watching this video. So, on this video, I'll be doing question 7 of November 2022 question paper, Physical Sciences, paper 1. The topic is the electrostatics. So, I'm going to read the statement and then proceed to answer the questions that follow. Let's go. A charged sphere M is suspended from a ceiling by a light inextensible insulated string. Another charged sphere N that has a mass of this and a charge of that hangs stationary vertically below sphere M. The centers of the spheres are 0.3 meters apart, as shown on the diagram. So we have this situation here. This is your ceiling, this one, which you have here. This is your ceiling, and then you have your sphere M that hangs from this ceiling with this string here. So you are told that another sphere N that has this mass and that charge hangs vertically below sphere M, right? And the distance between the centers of both spheres is 0.3 meters apart. Here is sphere M, the center of sphere M. Here is the center of sphere M. So the distance between these two spheres is 0.3 meters. Okay. So state Coulomb's law. So Coulomb's law, we all know it, right? Like this one. F is called K, Q1, Q2, all over R2. So this is your electrostatic force. This is your these are the charges, and this is your distance, or the square of a distance between the center of your spheres. You can state Coulomb's law by looking at it like this. So Coulomb's law states that the electrostatic force between two charges, right, is directly proportional to the product of these charges and inversely proportional to the square of the distance between two charges. That's what that is. It just tells you that this electrostatic force of yours is directly proportional to the product of these charges and inversely proportional to the square of the distance between them. That's Coulomb's law. I'm not going to write it down. Here is it. Straightforward. Let's go to the next one. 7.2. State whether the charge M is positive or negative. So they want us to tell whether this sphere here, the bigger sphere M, is positive or negative. So we're told that this sphere here hangs by this inextensible insulated string from this ceiling of ours, right? And we're told that this one, it was suspended, it's suspended, this one, and N hangs below, vertically below M, and it's not falling, it's not going up. But we know gravity is pulling it down, but it's not going down. It's not falling. It maintains its position from falling, right? So what keeps this sphere from falling? What this tells us, if gravity is pulling it down and it's not falling, that means another force is balancing gravity out, which pulls this sphere N upwards. And sphere N is pulled upwards by what? By sphere M. That's the only logical reason for sphere N to continue hanging vertically below this if it is not suspended like M is. So what do? So you say, okay, if there's gravity pulling it down, then this is pulled up by sphere M. And sphere N is positively charged. That means this one should have the opposite sign, so that the force between them is attraction, is pulling this guy upwards. So N is negatively charged. So we can say that 7.2, what did they say? State whether M is negative or positive. So M is negative. So that the force between the two is attraction and N is pulled upwards. Otherwise, if M was positive, then this sphere is going to be repelled down with the force. So the force of M on N was going to repel N downwards and falls, and the sphere N was going to fall and not just hangs there stationary. So So our m is negative. Let's go. 7.3. Draw a label free-body diagram of sphere N. So they want us to draw a label free-body diagram of sphere N. So, as I said when I was answering this question, we know for sure, 7.3, we know that one of the forces acting on N is gravity. So we say, okay, we have force of gravity here on N, right? Or we say weight, or we say mg. Any, same thing. What else do we have? We have the force of M on N, which pulls this one up, the attraction between the two. So we have the force of what? We have the electrostatic force of M on N pulling N upwards. So we have this force here. I'll just write this FA, force of attraction. So it's attracted towards M. So this is the free-body diagram of N. So these are the forces that are acting on N. And because this guy is stationary, that means these two are equal. Because it is stationary, which means it is not moved, which is these two forces are balanced out. It's at equilibrium. So which means your force of attraction is equal to your mg, which is your weight or your gravity, the force of gravity. So let's go. Calculate the magnitude of the charge on sphere M. So they want us to calculate the magnitude of the charge. Okay. 7.4. Calculate the magnitude of the charge on sphere M. They want us to calculate the magnitude of the charge on this sphere here. Right? Okay. So we know that this formula gives us the force, right? This is charge 1, this is charge 2, and the distance between them. So if you look at it, we don't have the electrostatic force between them. We didn't calculate it, right? We're not given. We're not given the electrostatic force between them, between the two charges. We have the constant. We have charge number 1. We can say it's this one here. Charge number 2 is what we don't have, which is M. We have the distance between them. So the only two missing things that we are not given are these two. This one and one of the charges. We have everything else. So what do we do? What we try to find is to find the magnitude of the electrostatic force, this part here, which is this force which is pulling this guy up, which the force at which the sphere N is pulled upwards by M. We can find this because we know that the force of attraction will be equal to weight because these two balance out, which is why this was equilibrium stationary. They're not moving. So, what do we do here? We say, okay, our force of attraction, which is the force which pulls N towards M, is equal to the weight of N, which is the force of gravity. So what do? We say, okay, we can find 7.4. We can say, okay, the force of attraction was equal to mg, right? So the force of attraction is equal to what? M, which is the mass of this object here. What is it? It's 2.04 of the sphere times 10 to the minus 3 kg times our gravitational acceleration, which is 9.8. So we have our force of attraction to be, then you can punch this straight on the calculator. Where is mine? So let's punch this on our calculator. 2.04 times 10 to the minus 3 times 9.8. This is equal to 0.02 newtons. So this is the weight. This is the weight of our sphere M, which is also equal to the force of attraction between the two. And that force of attraction between the two is our electrostatic force. So now we do have the electrostatic force to be what? To be 0.02. The only thing that we are missing is the charge, which we can calculate. Because we will say, okay, F is equal to KQ1, Q2, all over R squared. You have F, your electrostatic force, to be 0.02. Is equal to K, 9 times 10 to the 9, times Q1. What is our Q1? Our Q1 is 8.6 times 10 to the minus 8, right? Yes. Then Q2 all over R squared, which is R squared is the square of the distance between the two spheres. What is the distance between the centers of these things? 0.3. So 0.3 all squared. Then you punch this on. Oh, you don't punch it. You solve for Q2. What do? You say, okay, I can cross multiply this and that. So we have 0.02 times 0.3 all squared, right? Is equal to Q2. This you have 9 times 10 to the 9. 8.6 times 10 to the minus 8 is called Q2. So this is Q2. So you can solve whatever way you want. You want this one. You can punch this as a whole and then divide both sides with whatever answer that you get here. So 0.02 times 0.3 squared over 9 times 10 to the 9 times 8.6 times 10 to the minus 8. So your charge is 2.3 times 10, the magnitude of the charge, right? 2.3 times 10 to the minus 6 coulombs. So you can say, one can say, therefore, Q2 is equal to minus 2.3 micro coulombs. So this is our Q2. So we know this charge here now. So we can write it down and say, okay, M is 2.3 minus 2.3 times 10 to the minus 6 coulombs. That is your Q2. That's the magnitude of your Q2. So let's continue. 7.5. How does the electrostatic force that sphere M exerts on sphere N compares to that exerted by sphere N on sphere M? So they are asking, how does the force exerted by sphere M on N compares to that is exerted by sphere N on M? So you know from Newton 3 that using Newton 3 that this force exert, if this sphere here exerts some force on N, N will also exert the same force on M, but in opposite direction. That's Newton 3. So if sphere M exerts a force on sphere N will also exert equal magnitude force, but just in opposite direction. So the magnitude of the force, 7.5.1. So the magnitude of this force exerted by M on N compared to that exerted by N on M is equal. But the difference, the direction is opposite. So since M, the force exerted by M on N is upwards, which is attraction. N will also exert the equal force but downwards. So it will be attracting M downwards. So that's why we say they are equal forces but opposite direction. Then we move to the next question, which is now 7.6, which is we're looking at this diagram here. Point X, which is this point here, is vertically below the center of sphere M. So it is vertically below the center of sphere M, as shown on this diagram. The net electric field, so this point X here, right, which is vertically below sphere M, as you can see, it's placed here, this point X here. And this point of ours is 0.1 meters from sphere N, from the center of sphere N. Let me read this again. So let's go. Calculate the net electric field at X, right? So they want us to calculate the net electric field at X. So you know, electric field, here is electric field of yours. It's equal to electrostatic force experienced per unit charge, which is KQ over R squared. So the electric field is the electrostatic force experienced per unit charge. So it is the electrostatic force experienced by each charge. So they want us to calculate the net electric field at point X. How do you do this? First, you want to look at these situations, these separately. So what you want to do, you say, okay, let's say I have my M here, right? Here's M. And let's say I have my X here. Here's X. The distance between the centers of these two is this whole distance here, which is 0.4 meters, right? 0.4 meters. Also, let's look at these two now. So you have, so this is a separate diagram. So you have X here, which is this, and you have your sphere N here, which is this. The distance between the centers of these two is 0.1 meters. So, if we're saying we want the net electric field, we must find the net electric field at this point X because of M, and find the electric field at X because of M. And then you add the two to find the net electric field. I'll repeat this. To find the net electric field, what you need to do is to find the electric field at X because of due to M, and find the electric field at X again due to M, and then you add the two. That's how you do it. So you just have to look at one of these things separately. Look at this situation and find the electric field at X because of M, and find the electric field at X because of N, and then you add the two electric fields. And this is how you calculate the electric field. So, what are we going to do? We'll say, okay, we know that M is negative, right? So, since M is negative, you know the field lines at around M are like this. They are towards M. So these are your field lines around M. So, since these are your field lines around M, so the electric field felt by X because of M is upwards towards M. So M So the electric, if you extend this all the way, right, you find that x, your point x here, the electric field that is feeling because of M is upwards towards that direction. This is the electric field of M on X. So X is feeling this electric field, this field, pulling it upwards towards M. So this is the electric field in which X is feeling because of M. So we can calculate it by saying, okay, E, electric field of M on X is equal to KQ over R squared. What is your K? 9 times 10 to the 9 times Q. The Q is what we just calculated, that, which is 2.3 times 10 to the minus 6 all over R squared, which is, what is the distance between the two? The distance between the two is 0.4, which is what we just discovered. So we say 0.4 all squared. So this is the electric field of M on X. So let's do that. So we say 9 times 10 to the 9 times 2.3 times 10 to the minus 6 over 0.4 squared. So we have 1.29 times 10 to the 5. What are the units of electric field? It's force over charge, which is newtons per coulomb. And electric field is a vector. So this one is newtons per coulomb, which is a vector, so it has magnitude and direction. So this is the magnitude, and the direction is upwards. This is upwards. So the electric field at X due to M is this upwards. You do the same thing for N. You say, okay, N is what? Is positive. The electric field lines from N are like, look something like this. Out, 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 out. So, if you look here at X, the electric field felt by X due to N is away from X downwards. So you've established the direction of the electric field at X due to N. Then you just calculate it and give it its own direction. So you say E, electric field of N at X is same formula, KQ over R squared, which is equal to 9 times 10 to the 9 times Q. What is Q? It is the charge of N, which is what we were given. It would be 8.6 times 10 to the minus 8 all over R squared. What is R? The distance between the X and the center of N, which is 0.1 all squared. So the electric field of N at X is equal to the answer of this. So it's 7.74 times 10 to the 4 newtons per coulomb, and it's downwards because we said that the electric field at this point due to N is downwards. You can see the electric field line. Then what do you do at this point? To find the net electric field, you just add the two. It's up to you to decide which one is negative according to your own coordinate system. But for simplicity, we can say the upwards is positive and the downwards is negative. So to find the net electric field, you must add the two. And that is what we are going to do right now. So we had that the electric field at X due to M was this one here, and the electric field at N due to X at X due to N is this one here. So now what we're asked to find is the net electric field at E at X. So what do? We say now, to find the net electric field, we must add these two electric fields that are there, that are felt by X. Then you will find the resultant electric field. So you say, okay, E net is equal to E of M, the electric field of M at X, plus the electric field of N at X. Right? So what do? You say, okay, what was this? So this one, we say is upwards, right? So it's positive. So it's going to be positive 1.29 times 10 to the positive 5 plus the negative of that, minus 7.74. We say it's negative because it's going down, times 10 to the power 4. Then punch this on our calculator to find that E net is equal to 1.29 times 10 to the power 5 plus negative 7.74 times 10 to the power 4. This is equal to 5.16 times 10 to the power 4 newtons per coulomb. And since it's positive, it should be going upwards, because we said the positive one is up. So the resultant electric field is upwards. So this is how you do this question. I hope it is clear. I'm done.